Hello, my chemistry friends. We are going to take some time to go through some of the questions that you guys are doing in class today to make sure you understand what you're doing. So a wise idea to use this video would be to take a look at your question, see if you can answer it, and then you can put this on pause, and then you can go back and check your answers. So please use your pause freely here. Let's look at this first question. What is the difference between ionic bonding and covalent bonding? So of course, I'm just going to write on the screen so you have a better idea of what's going on. So let's look at ionic bonding first. So you have ionic, you've got a metal plus a nonmetal. And so basically, if you have a metal in a compound, it is going to be ionic because covalent is a nonmetal plus a nonmetal. So just remember also, covalent compounds, the electrons are actually shared, where these ionic compounds, the electrons are given and taken. So remember, it's not like, oh, here's my electron. It's like, give me all your electrons. It's more of a take than it is a give. Next question, briefly explain how to name the following. So the reason why I wanted you to do this is so that you can go back to remembering if you can explain how, then you can name any acid or base, or you can name any ionic compound. So first off, let's look at A. We've got an H here, so that tells us it's an acid. And we have SO4, so this tells us it's an oxyacid, not a binary acid. So since it's an oxyacid, we do not use hydro, so there's no hydro here. We look up sulfate on our periodic table chart, and we see it as 8, which translates into ick, because I ate Brussels sprouts and it was ick. So therefore, we are going to name this sulfic or sulfuric acid. You can do either one, sulfic acid. I usually say sulfuric acid because that's kind of more of the common name for it, but sulfic acid works and it's just fine. The second one, we have a calcium, so it's a metal, so it must be ionic. So therefore, we write the name of the metal. Okay, so a metal here. And we have a polyatomic. So the beauty is for polyatomics, we don't need to change the endings or anything. We just write what the polyatomic is. And this polyatomic is OH minus, which is hydroxide. So we are simply naming calcium hydroxide. Be sure to not put Roman numerals in there because calcium is an alkali earth metal. So therefore, it has 2 valence electrons all the time. This next one, we're going to see a nonmetal with a nonmetal. So we have 2 nonmetals. And if we have 2 nonmetals, we know it's a covalent compound. So therefore, if it's covalent, we're going to use those prefixes. Woo-hoo. So sometimes people like to get prefix happy and they use them on everything. You can only use them on covalent. So notice there's a 2 here. So we say dinitrogen. And there's a 1 O. So we have to say mono on the second word. We don't say mono on the first word. But we say dinitrogen monoxide. I know it's kind of weird. Monooxide. It's weird, but just put it together. Think about carbon monoxide. You say that all the time. Maybe not all the time. Take that back. All right. This next one, we've got a copper and we've got an oxygen. So copper is a metal. Therefore, we know it's ionic. Copper is a transition metal, so it's going to have more than one potential charge. So we have to figure out the Roman numeral. We are going to use a Roman numeral because it's a transition metal. And so we've got to figure that out. Oxygen has a 2 minus charge. And if there's 1 oxygen and only 1 copper, then copper must have a 2 plus charge. So therefore, we write copper and then 2 in parentheses because that's the charge on copper, oxide. So copper 2 oxide. Let's go on to the next ones. We're just going to name the following compounds here. So let's look at A. We've got strontium, so it's ionic. So we're just going to say strontium and fluorine. We want to change to fluoride because with being ionic, we just use IDE. Strontium fluoride. No need for Roman numerals. Same thing with barium. We've got a metal and a nonmetal. Barium is an alkali earth metal, so it's not a transition metal. We have no need for a Roman numeral then, so we have barium sulfide. Okay, titanium, it is a transition metal, so we've got to look at what charge it's going to have. And in this case, titanium, we have chlorine has a -1 charge. There's 4 chlorines. So to take out a -4 overall for the chlorines, we only have 1 titanium. So that 1 titanium must be a +4 charge. So therefore, we're going to write titanium, and we'll put, again, the charge in parentheses, which is IV, 1 before 5, chloride. Same thing with nickel. Don't get this confused with nitrogen. Nitrogen is just an N. Nickel here, we have a transition metal. And if oxygen's a 2- charge, look where that 2 came from. So nickel must be a 3+ charge. So we have nickel 3 oxide. Right here, don't think that a lot of people thought and looked at this right away and they said, oh, it's sulfite. This isn't sulfite because it's not an ion. There's no charge up here. It is simply a covalent compound. And so we're going to name it sulfur. Remember, we don't say monosulfur. Sulfur trioxide. The reason why we don't say monosulfur is we don't use the word or the prefix mono in the first word. Okay, this last one, lead, is a transition metal. So therefore, we've got to figure out the charge on it. Nitrate, the whole nitrate has a -1 charge. So that 2 must have come from lead being a +2. So we have lead 2, and then we just write nitrate. You guys are totally getting the hang of this more and more, I can tell. All right. Now we want to write the chemical formula. So now we have the name and we want to zap it into the chemical formula. Some people have more trouble with this. If you can use your periodic table well, it'll be a piece of cake. Now with zinc oxide, we have Zn and O. And then we look at the charges. And if you look on the back of your periodic table, zinc always has a 2+ charge, although it is a transition metal. Oxygen has a 2- charge, so they crisscross and they cancel. So we have ZnO. Calcium phosphate, we have calcium, and then PO4. Phosphate has a 3- charge. Calcium has a 2+ charge, so we crisscross. So we get Ca3PO4 2, calcium phosphate. Sodium iodide, we have sodium and iodine. Sodium has a -1 charge. Sodium has a +1 charge. Iodine has a -1 charge. Crisscross, and we just get NaI. Manganese dioxide, you guys, so many people wrote Mg today. Manganese is Mn, and it has a 4+ charge because of the Roman numeral here. Oxygen has a 2- charge. So if I crisscross, this gets a little tricky because I'm going to get Mn2O4. But look, I can reduce this because 2 and 4 would just be like if you have a fraction. So 2 can go into 2 one time, 2 can go into 4 2 times. So my final answer is MnO2. And finally, aluminum acetate, I have aluminum. And acetate is C2H3O2. And it's on the back of your periodic table. It's one that we added. It has a - charge, and aluminum has a 3+ charge. So to write it, we're going to write Al with our parentheses, C2H3O2, and we're going to put the 3 from the aluminum on the outside of the parentheses. Let's try the next ones here. We've got disulfur tetrachloride. So those prefixes are telling us, hey, we're going to have an ionic compound. So we have sulfur, di means 2, chloride, tetra means 4, S2Cl4. Now here's the thing, a lot of us want to reduce this. We want to be careful when we reduce covalence. We don't reduce covalence like we do ionics. And it's because this sulfur trichloride would look something like this. So its molecule is going to be a little bit different. So I just want you to realize that a lot of times covalence, we don't reduce down. Magnesium nitrate, we do have magnesium this time. It does have a 2+ charge. Nitrite, notice that ite is an NO2 with a 1-. If we crisscross, we're going to get magnesium and then put nitrite in parentheses with a 2 on the outside from magnesium. Hydronitric acid, we see the acid and we know it's an H right away. We look and we see that hydro, and that hydro tells us it's only one element. So it's HN. Hydrogen has a +1 charge. Nitrogen has a 3-, so therefore our final answer is H3N. Nitrous acid comes from ite, and so we know it's an acid, so it's an H. We want to look up nitrite, which is NO2, and it has a -1 charge. So hydrogen having a +1 charge, and we can just have HNO2. Nitric acid comes from ate. We know it's an acid. Then we write our nitrate, and nitrate has a -1 charge, hydrogen a +1, so we have HNO3. All right, here comes a little bit tougher ones with the VSEPR theory. So let's look at selenium dioxide. First off, you want to check, and let's write what selenium dioxide would be. SeO2, okay? Selenium, if you check your periodic table, has 6 valence electrons. Oxygen has 6 valence electrons, but there's 2 oxygens here. So we add 6 and 12, and our magic number here is 18 electrons. This is what we're going for, to get 18 electrons. Our second step is we're going to create our skeletal structure. So we put our selenium in the middle, and we're going to put, fill our octet rule, meaning that they're all the atoms have 8 valence electrons. If we look at this oxygen, we've got 2, 4, 6, 8. Selenium, we've got 2, 4, 6, 8. This oxygen, we've got 2, 4, 6, 8. Remember, every bond is equal to 2 electrons. So total, we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. If you have more electrons than you need for your magic number, then you've got to make some double bonds. So we're going to remove electrons from the selenium and from one of the oxygens. And in this case, it doesn't matter which oxygen it is. So we're going to, then create a double bond over here. Now you have to understand this oxygen still fills the octet rule. 2, 4, 6, 8. Here's selenium. 2, 4, 6, 8. Here's oxygen. 2, 4, 6, 8. So we're still working right. Total, we've got 2, 4, 6, 8, 10, 12, 14, 16, 18. We've hit our magic number. So now we want to look at the hybridization, and that is the number of things attached. And those things could be a lone pair like we have here. So we do have a lone pair of electrons here. So we actually have 1, 2, 3 things attached. Therefore, S counts as one thing, P counts as one, so we need an sp2 because sp2 is 3 things attached. Once we look at the molecular shape, you want to use this chart right here, and you'll get to use this all the time on quizzes and tests and everything. So you look at sp2 and you see which one has 2 bonds and a lone pair. Look at the molecular shape, and it is bent. So you're just going to write bent. All right, sulfur hexafluoride. So sulfur and then hexafluoride. Hexa is 6. So how many valence electrons for sulfur is 6? Fluorine has 7 valence electrons, and there's 6 of them. So our total is 48 electrons. Now this is weird because this time sulfur can actually hold all 6 fluorines, and the reason is sulfur is in the 3rd energy level or below. So therefore it can hold all 6, and each fluorine will have 6 electrons around it in addition to the bond that it contains. And if you count all of those electrons and all of those bonds, you're going to get 48 electrons, which is our magic number. So hybridization, we have 6 things attached. So we want to do S, which is 1, P3, that's 4 things, D, 2, look, S, P3, D2, that's 6 things. So therefore we have sp3d2. We look on the back side of this handy little sheet, and we notice that they're all bonded, so we're going to have what's called an octahedral. Octahedral is the shape. Okay. All right, let's take a look at the next ones. This one we have an ion. So we have phosphorus tetraoxide. So we've got our phosphate ion basically. So phosphorus has 5 valence electrons, oxygen has 6 each, and there's 4. But then something interesting, that 3 minus is actually adding more electrons. So we're going to add 3 more electrons. So we have basically 24 plus 5 is 29, plus 3 is 32. So 32 is our magic number here. So we're going to put phosphorus in the middle and 4 oxygens around. And we're going to make our skeletal structure. And if I count them total, I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. That's the number of electrons I need, so I'm all set. How many things are attached to phosphorus? There's 4 things attached. So we have an sp3. S is 1 with 3 p's. Our molecular shape, again, we look at our handy dandy chart, and an sp3, and we have all bonds, so we're going to have a good old tetrahedral. Okay, so our molecular shape will be tetrahedral. All right, carbon tetrachloride. Okay, so we've got our carbon and chlorines, and let's find our magic number here that we're going to need. So carbon has 4 valence electrons, and chlorine has 7, and there's 4 chlorines. So we're going to have 32 electrons again. So it's going to look very similar to what you see above. And basically, you're going to have the same hybridization and the same molecular shape as you see above, because you have 4 things attached. So an sp3 and a good old tetrahedral, because you have no lone pairs or anything of that nature. All right, let's do this last Vesper here, carbon dioxide. So first off, carbon has 4 valence electrons. Oxygen has 6, and there's 2 because carbon dioxide is CO2. So therefore, we've got 16 electrons we want to deal with. So we're going to have our skeleton structure here, and we're going to fill our octet rule. So we fill our octet rule. And if we count them all now, we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. We have 20 electrons, so we have more than enough. So what we're going to do is bust out our eraser here. And I'm going to take off 2 electrons from the oxygen and make a double bond on each side. So let's see if this will work if I make a double bond on each side. So I'll go back to my pen. Okay, and so now, and sorry, you can kind of see I left that on there. That is a big no-no. Okay, so I've got 2, 4, 6, 8, 2, 4, 6, 8. If I add all those together, I have 16 electrons accounted for. My hybridization is a little bit different because look, my carbon's only attached to 2 things. So I simply have an sp hybridization. If I look at my sp hybridizations, basically you only have one option for a shape, and that is simply linear. All right, let's go to predicting products and balancing for these following reactions. So this first reaction is a double replacement reaction. And so we're just going to switch our metals. So let's put silver with chloride here. Remember, we don't take any baggage over, and silver always has a +1 charge, chlorine has a -1 charge. And we're going to put sodium with nitrate. And sodium has a +1 charge, nitrate has a -1 charge. So what you're going to do is for double replacement, you're going to use your solubility chart. So you want to use your solubility chart for your product. So you're going to look up silver chloride and sodium nitrate. You're going to find that silver chloride's insoluble and silver nitrate's soluble. So therefore, this reaction will in fact run. So and it's actually already balanced. So we don't even need to balance it any further. Now we have a combustion reaction. Cb is combustion. So we have C6H6 plus O2, and we're going to get CO2 and water because that's our products always for a combustion reaction. Now, to balance combustion, we use the Cho method. So we have 6 carbons, and we put 6 carbons. But then I'm thinking, hey, we have 6 hydrogens. If I have to put a 3 here, then I'm going to have an odd number of oxygens. So what I realize is I'm going to put a 2 in front of my hydrocarbon when I realize that it's just simply not going to work with the number of oxygens. So now I have 12 carbons. Then I do my hydrogens. I have 12 hydrogens. And now I have 12 times 2 is 24, plus 6 is 30. I have 30 oxygens, so I need to put 15 here because that's half of 30. This is a decomposition reaction. And although it's not on this particular paper, I always put this little table right here so you can see this. And first off, you've got a chlorate. So if you have a chlorate, you have to figure out, hey, it breaks into O2 and a Cl and a blank Cl. That blank is going to be your metal. So we're going to have zinc chloride. Zinc has a 2+ charge, chlorine a 1-. And we're going to combine that with O2. So therefore, let's balance this here. We have 2 chlorines and 6 oxygens. So we get 6 oxygens on this side and our zincs balance on either side. Now we have simply a composition reaction. So we're just going to put a metal and a non-metal together, but be careful because I did this purposely and put the oxygen first because some of you like to just put whatever's first, and we don't put oxygen first because it's a non-metal. So we must put our metal first, and we have ALO, and we don't take any baggage over with us, so we're not going to bring that too. But we do have to make a new relationship. So we have Al is a 3+ and O is a 2-. So I put Al2O3. Here's a 3-2 combination with the oxygen. So I make it 6 oxygens here, 6 oxygens here, but then that gives us 4 aluminums on either side. All right, last section here, we've got a double replacement again. So we're going to change our metals around. So we're going to put potassium is going to go with nitrate. And remember, you don't take over any baggage. Potassium has a +1 charge, nitrate a -1 charge, so it's good. Okay, and we're going to put lead with iodide. Now, lead does have, you can tell lead's charge because nitrate has a -1 charge, and there's a 2 right here. So lead's charge must be a +2. So if lead's a +2 and iodine's a -1, then we have PbI2. Now we need to check to see if that's going to work. So we have to check our solubility chart. And we look up KNO3, and KNO3 nitrates are always soluble, you guys. And then iodide, so we look up lead iodide, and we find that it is actually insoluble. So this reaction will work, and we just need to balance it. So we have 2 nitrates here on this side. So we need 2 nitrates here. Now we have 2 potassiums. And now we get 2 iodines, and we have 2 iodines over here already. Our lead is 1, our lead is 1. Okay, now we have an acid-base reaction. And the way that we know that is there's an OH and an H, and together those make water. And then we're going to put our lithium with our chlorine, and lithium's a +1, chlorine's a -1. So we're good already, we're done. But we do have to balance and just check. So we do have 2 hydrogens on this side and 1 oxygen, 2 hydrogens and 1 oxygen, lithium, chlorine. So we're all balanced already. Combustion again. Combustion, we always know the products are carbon dioxide and water. We're going to use the Cho method here. So we're going to balance our carbons first, and we find again that hydrogen is going to create a 3 over here, and that's going to make an odd number oxygen. So let's put a 2 in front of our hydrocarbon. Now we have 4 carbons. We have 12 hydrogens, and now we look at our oxygens. We have 8 plus 6. We have 14 oxygens, so we're going to put a 7 here. For 7 times 2 is 14. And our last reaction is a single replacement. So for single replacement, we're going to use our activity series chart. So we have our single is a metal. So we're going to compare that to the other metal in our compound. So we're going to compare on this chart iron to copper. And since iron's single, we have to see if iron can in fact knock out copper. And iron is Fe, copper is Cu, and Fe is above Cu, so it can happen. So we're going to put iron with nitrate and leave copper hanging. Now we do have to check iron here is not, like there's no indication of the charge of iron here. So if we look at our the back of our periodic table, iron is typically a 2+ or a 3+, So we're going to take our lowest and assume iron's a 2+. And so then we'll have an FeNO3 2. So NO3 2, NO3 2, copper, copper, iron, iron, and we're balanced. All right, guys. That is basically all of the problems on that timeout and review sheet. So you guys can do this. You're getting better and better and better, and you can do tough things. Just keep going. I'll talk to you guys later.